Okay, so let's go. So yes, so the problem is about delta plus one coloring. Right? It's a very easy problem. You're given a graph. You want to give colors to the vertices such that adjacent vertices receive different colors. And it's very important that we use delta plus one colors because delta is the maximum degree. Because it means that if you take any partial coloring, you can like look at a vertex. It always has one color that's not already used by its neighbors. So it means that for any partial coloring, you can always extend it to a total coloring, and you have like a very simple linear time algorithm to do this. So it's like a very easy problem. But it gets more interesting if you kind of change perspective and you try to do it with distributed algorithms. What I mean by that is that you see the input graph as a communication network, and the vertices are computers. They talk to each other using the edges of the graph. And so at the beginning, you only know, your neighbors in the graph. You talk, you learn more and more. And the question is, after how many rounds of communication will you be able to make a decision about your color such that it's consistent with everybody? And of course, you want to minimize like the number of rounds of communication. Like it kind of measures how much you need to learn about the graph, and you want this to be as small as possible. And so it's kind of like a classic problem in the distributed literature because it models very well like the kind of problem we run into in this model. Like think about two nodes that try to take a color. You really want to find ways to efficiently avoid the situation where they both try to take the same color at the same time, right? If they do it repeatedly, your algorithm is going to be slow. So you need to find ways to get around that. And so like there is a very easy like log and round algorithm to do it by just trying random colors. And I just suggest like you try to think about that. It's not very difficult. But this is like the first step, and there has been a lot of work that I'm not gonna like really summarize because it's I'm not going to tell you about everything because it's going to be a bit long and boring. But the complexity now looks a bit like this. So the value of delta is kind of important. If it's with some constants, then you have a log star and round algorithm. And this has been known from like the very beginning of local algorithms, pretty much. So extremely fast algorithm, and this is actually tight. Like you can't do any faster than log star rounds, right? And if you go slightly beyond constant, so like between delta is like between a constant and some polylog n, the algorithm is like log n rounds. So it's like exponentially faster than what you get if you do like the stupid thing. And like getting there was easy. It took like 20 years maybe. And what's interesting is that like if you go even like if delta is just above polylog n, then the algorithm gets insanely fast again. You get like a log star algorithm again. And I mean, this is maybe a bit counterintuitive because like delta, kind of in some sense is the number of conflicts you might expect in the graph. Like if you have higher delta, you should have more conflicts, so it feels like it should be more difficult. But actually, this is not what's happened. Like for some, like it just gets easier when delta is larger. I mean, like these are not like we don't have lower bounds for this, so maybe you can actually push this down. But like currently, it looks like that. And
wait, sorry, is it possible to get longest star and rounds for the entire regime, nothing ruling that down?
No. So like you like the only kind of lower bound we have when we leave constant degrees is that the gap between the gap between randomized and deterministic should be exponential. But that's pretty much all we know. So if you find like we don't even know like that it's not possible to do log star deterministically. Like I don't really think it's possible, but we don't have lower bounds for it. When delta is large, when delta is constant, we have it. And actually, like yeah, the lower bound here is just a constant, but it really doesn't give us anything. So even there, this is not tight.
Wait, but that's weird. I expect less colors, the problem is harder, and you have this range.
Yeah. So this is very weird. Like, kind of, what's happening is that when you have a high degree, so like, in some sense, like, okay, I guess I'll get to that. But the thing is that you kind of have more ability to communicate as well, because you have more edges. Right? Because delta is also the number of colors that you have.
Right.
So if you don't have as if you're not close to delta degree, then you're easy to color. And if you have delta degree, then you have a lot of ability to communicate, which helps a lot. It's kind of what's happening here. And for this talk, we're really just going to care about this range where delta is large. And why is that? Well, if you look at how the congest algorithm works, you have some coloring procedure that just, well, it's not going to color all the nodes, but it's going to ensure that, like the palettes, even if you color all of your neighbors, they're still going to have like a significant amount of colors left. And when you get to that, it's actually like trying random colors is actually going to, if you try colors, and maybe you don't get color, then if you don't get color, then you just try more colors more aggressively. And the thing is that, like this type of condition means that your palette is never going to shrink too much, but the number of uncolored neighbors you have is going to like go down very quickly. And so every time you fail to get color, the next round, you're actually more likely to get color. And so like you kind of get more and more likely, and after a log style round, if you do it carefully, you're colored with high probability. I don't really want to get too much into the details, but that's kind of like the rough scheme. And
sorry, what is the palette for?
The palette, yes, like you remember this set at the beginning. So you look at the current coloring, you take delta plus one, and you remove all the colors used by your neighbors so far. Yeah.
Okay.
So that's what the palettes are. And the point is that like if you have multiple neighbors that take the same color, then you kind of get one color that's never going to leave your palette. So it can like it's possible that it's never going to like shrink to like just one color, more or less. And yeah, so the problem with these algorithms, at least the problem I have, is that to go through this, you kind of need to compute these palettes, everyone. It means you need to learn kind of the colors of all of your neighbors each round to do this algorithm. And okay, this is not really a problem in the congest model. The congest model itself doesn't really capture it. But if you think about like large networks, it might not be like a very reasonable assumption that you're able to talk with delta many neighbors at the same time. Like we usually assume that like in sublinear models, polylog is fine. Like this is a reasonable amount. Everything above that is unreasonable. If you take this perspective, then talking with more than polylog neighbors at the same time sounds a bit unreasonable. And it's really like, if you put this constraint that you don't talk with all of your neighbors, because you can't really compute your palette, it really breaks all the algorithms. And so the question that we had was, can we still do delta plus one coloring, but without, like, crucially, without talking with all of your neighbors, or just talking with like a reasonable amount of neighbors? And this question really connects to, can we avoid computing the palettes, right? And this is something like even combinatorially for general algorithms that we would like to understand, because if you understand when you can avoid and how you can avoid computing these sets, maybe you can get faster algorithms in a bunch of settings. And yeah, so it sounds a bit like impossible at the beginning, because like, why would you be able to, how could you safely take a color if you don't know what your neighbors are doing? But actually, like, there is hope, and so the hope is this Sparsification theorem by Asadish and Kana, two of whom in the room. And it's like an amazing theorem that says, if you're given a graph, and for every vertex you sample log n colors at random, then with high probability, you will be able to color the graph using only colors from those lists, right? Like vertex V is only using a color that's going to be in the random list. That's what we call a list color. And yeah, I just want to like, it sounds like a kind of an insane theorem. Like delta plus one, at the beginning, it's supposed to be easy because you have so many options, right? You always have one more color to choose from than neighbors. And what this theorem says is that actually, if you reduce your set of options to this very small set of log n colors, somehow the coloring still exists. It's very surprising when you just look at it like that. Yeah, and I mean, we'll get to how, like, why this actually works. And the thing is that the colors are random. And this is why, like, how you can, like, reduce the options like this. But even without, like, going too much into the details of how this works now, it's still useful as like a black box result, because once you've committed to use small sets of colors, then you only care about very few edges in the graph. And the reason is that you only care about an edge when the two lists at the two endpoints have an intersection. Otherwise, you're only going to have a conflict. And because the lists are random and very small, it's very unlikely that you have many neighbors that sampled colors colliding with yours, right? So if you look at what I'm calling here the sparsified graph that only contains like the crucial edges that we need to care about where the list intersects, it's not difficult to show that this is a sparse graph, right? And so this already gives you like a very simple and nice algorithms in a bunch of settings. And and so the algorithm roughly goes always like the same. You sample the list, then you try to compute the sparsified graph, and you just find the least coloring of that sparsified graph. And how you do this exactly depends on the exact model you care about, but it's like the general scheme given by the palette sparsification theorem. And and so what we would like to do is, okay, just do this in congest. Can we use that to get a congest algorithm where we only need to talk on the sparsified graph, because this is like the maximum degree of this graph is polylog. So if I have a congest algorithm to find this list coloring, then I'm only talking with polylog many neighbors, right? And I can solve the question I had at the beginning, right? And so the issue is this: well, sampling the list is fine. Like every vertex can sample its own list. Computing the sparsified graph, well, I don't know, you can make assumptions about this, like either the graph is given at the beginning, or you can see the public randomness of your neighbors, things like that. So this is doable. And what's really annoying is that finding the list coloring is actually not easy. Like at least the coloring procedure of the palette sparsification theorem doesn't work in congest. And the reason is, well, they have like something that's very sequential. They take a bunch of vertices, color them, and then they switch to another bunch of vertices and color them, and go on like that. So it doesn't really work well in congest. And even worse, like they use the probabilistic method. So it's just purely existential arguments about the existence of coloring, which can be fine sometime, but it's doesn't work. Like at least it's not clear how you could make this work in congest. And so the problem we have to solve is really this: can we find the least coloring of the sparsified graph?
Wait, can you say how can you find G2 though in contours?
Yes, so that's a good question. So we just assume that the edges are given and that like I assume this is in the input kind of. So we're kind of cheating. Like one way you could do it is say I can see the random colors, like nodes have public randomness, and I can see. Yeah. It's not a big deal in our assumptions. Like for the applications that we have, you can kind of get rid of that.
Can you say because we cannot share the these algorithms, I guess, require a lot of randomness, and you cannot just share it without talking over algorithms, or like somebody just send it to everyone. Yes, so
it's a good point. So one of the applications you actually have a global communication. So there you can cheat and synchronize everybody. The other application is more like you can do some kind of aggregation, you can broadcast to it's like every node is kind of a tree to the neighbors. And so you can't really do individual messages to your neighbors, but you can do aggregation, and you can do like very simple things where you send all of your colors. All right, you spread your log n colors sampled on the tree, and then the leaves, they're gonna correspond to the edges of the graph you're trying to color, and those can check for intersections there, and then you just gather back the information. So like in this model, just the way it's defined, it works. But yeah, so you have to make some this part is not so clear, just in congest. Absolutely. Okay, so the theorem is this. You have a graph and you sample so slightly more colors, log square colors instead of log n. And you do have, so assuming like either the sparsified graph is given or something like we just discussed, you can compute distributively the least coloring that corresponds to what you've sampled in log square delta rounds, which is pretty fast for a distributed algorithm. It's not as fast as log star, but still reasonably fast. And so it's a congest algorithm. You only use small messages. And it only communicates on, well, the edges of the sparsified graph. So over the whole algorithm, you're only going to talk to log to the far many neighbors, which kind of really solves the question we had at the beginning. Okay. So yeah, this is the theorem, and we only really care about like large value of deltas because like when delta is small, you can just run the convex algorithm anyway. And so it gives like a log n running time. But let's not really care about this. Okay, so for the applications here, so as I said, like so this model, it's like congest. You can talk with everybody in the network. You're not restricted to talk with just your neighbors. Just the like one big constraint here is that you can't talk with more than polynomials at the same time. And so you can just like use a trick to remove the public randomness and then run our algorithm in this model. And the cluster graph is something that arises very naturally when you try to compress edges, for instance. Like for some reason you've compressed edges and you care about like, the nodes in the graph where you did these compressions, but you still have to communicate on the communication graph. Like you have like these two vertices. You didn't get rid of the edge in the middle, so you still have to. You're trying to color like the two vertices together, but you still have to make them equal. And so if you push this a little further, you get into a situation where every vertex that you try to color is actually kind of a tree, a set of vertices in the communication graph. And this has arisen very naturally a bunch of settings for distributed algorithms. Yeah, so we get like the first polynomial rounds algorithm studies. And I think the theorem is also nice for a bunch of other reasons, including that like so some parts of the palette sparsification theorem were already distributed, and we've kind of make it fully distributed. And I hope I'll convince you that it's not so surprising that it works. It just like it requires like a small shift in perspective. And then you could also like explore, okay, like kind of the intersection between sublinear algorithms, streamings or like having low message complexity, these kind of things, and merge it with the distributed literature, this kind of thing. And so we're kind of in between these two worlds, and I think it's like also a nice direction. Okay, so right. So for the rest of the talk, I'm going to try to tell you a little bit about how this theorem works. Is there any questions so far? No? Hopefully this is good. Okay, so let's start with an easy one. I'm giving you two delta colors, so much more than what you're supposed to do. And like this is just to get some idea of how we prove this palette sparsification theorem, this even distributively. And the point I want to make is that then you'll get the congest algorithm. And to make this concrete, so let's think about the following congest algorithm. As long as you're not colored, you just sample a color in two delta. And notice that this step really does not depend on whatever happened in the algorithm before. It's what I mean by non-adaptive. And then you just check, okay, is this in my palette? Is one of my colored neighbors using it? And was that color like sampled by a non-colored neighbor? Is someone also trying to use that color at the same time? Right? If not, well, I can just safely pick the color. But that's like the whole algorithm. And so it's not very difficult to see. You have delta neighbors, and they each block one color. So whatever, like regardless of what your neighbors do, you always have 1/2 probability of getting color each round, right? So after log n rounds, all the nodes are colored with high probability. And you might say, okay, you do need to compute the palette and like check these things with all of your neighbors. And you'd be right. But because the samplings are non-adaptive, and you know that the algorithm is looking around, you can kind of sample all the colors at the beginning before you even look at the graph, right? And you make these log n samples that you've just done, like this is your random list. And okay, again, with this assumption that you can see the list of your neighbors, when you try to run this algorithm, you know that you only need to check this condition, you only need to talk with the neighbors where there is an intersection between the two lists, right? So that's how you get like distributed palette specification for two delta colors.
I can already see the colors that my neighbors picked in order. And like, can each B just run the algorithm on its own? We can not do anything in one round and done.
Good.
I can look at everything, right, globally.
Yeah, but you like, so it's a very good question. So you don't know which of the colors, you know which colors they're going to try, but you don't know when they're going to stop because you don't know all of the neighbors of your neighbor.
You know the neighbors of the neighbors.
Yeah.
No, but the public ranking is here. Like, what is your assumption about? Like, because public here, my assumption is that I know everyone's randomness, like not just my neighbors.
But not be finished.
Yeah.
But I don't know the actual. I don't know the graph. Oh, okay, very good. Thank you.
Yeah, we really just know your neighbors.
Okay.
So you just need to like communicate to synchronize on which color you're actually using.
Right. Thank you.
Okay, so yeah, and this very simple algorithm generalizes to what we call locally sparse vertices. I don't want to say much about those. They are just like vertices where you have like a lot of missing edges in the inside, and so you can like by just trying random colors, like a lot of neighbors are going to pick the same color, and so you're losing some colors, but you're losing twice as many neighbors, and this creates like an excess in your list, and you kind of end up in the same situation as you were in this two delta color. You always have like a constant fraction of the color space that's available. Okay, so okay, maybe this is not completely clear. Like making this step is it's not trivial, but I just want to say like this is not too difficult, and at least like this was already done in the palette specification theory. So let's just assume this is easy. And why do we care about that? Well, you have a decomposition theorem, like a structural theorem about color, like graphs coloring. And it says that you can split any graph between, so what I just said, locally sparse vertices, that we're not going to care too much about because it's like two delta coloring, and the almost splits. And those are really like what's going to cause trouble for us. So what's an almost split? Well, and the name is self-explanatory. It's like it really looks like a click. It's a very dense cluster, but you could have some edges missing on the inside, which means that the click could be like slightly larger, and you could have like some edges going to the outside as well. So it's not really a click. Like you have to deal with these things that make it like not a click, but it's not also too different from a click. It's really an enormous click. And like this parameter kind of decides like where you put the threshold between what you consider a click and what you consider not a click. Right? Is that definition sort of clear? Yeah. Okay, so the challenge really is coloring these dense clusters. And okay, let's just think of a click, a real click, not even an almost click for now. How did they do it in the palette specification theory? Like every vertex was a different color, right? So you're looking for a perfect match, and the edges of the graph are, describing which colors are in the list of each vertex. If green is in the list of B, I put the edge between green and B. And notice that like this is a random graph because like I sample green in the list of B with probability like log n over delta. So I have like this random bipartite graph, and finding a coloring for this graph is really just like finding the perfect matching. Right? Yeah. So once you look at things this way, what you can use is like this whole theorem that gives you like a very exact condition of the existence of perfect matches. And in random graphs, like you can show that with high probability, this condition is going to be satisfied. So it's not very hard to see like, for a click that it works. It's more complicated when you get to almost clicks, but already like this part of the argument, you see like it's existential. So we don't have like this nice congest algorithm when we sample maladaptive colors and things like that. And that's what we would like. So we want to like replace this part of the argument with something where we say like I sample color, and if it works, I do this. If it doesn't work, I do that. Right? Okay, so let's think about like even simpler situation. I have just one uncolored vertex in the click. It doesn't really look like a click, but it's a click. I have one uncolored vertex, which means there is one free color that's not used. So the green color, and I want to design so that this type of congest algorithm we talked about. So what you can do is just sample a uniform color, and most likely it's going to be used. Like you'd be very lucky if you get green. And if it's used, well, it means that I've sampled, like this guy has sampled red, and this guy used red. So there must be an edge in the Sparsified graph. And these two nodes must have red in the list. So there's an edge here. And then I can just do it again. So I find this blue guy. And you repeat this a bunch of times, and eventually you're going to find the vertex that's going to sample green. Right? And when that happens, well, you can just use green to color this guy, and use blue to color this guy, and use red to color the one colored vertex. Right? And you end up with this. And so you've colored this uncolored vertex. It's kind of like a, yeah?
I'm sorry, but if you're doing it, you said you're coloring a click first, and then you talk about the epsilon sparse, but
yeah, maybe that was a bad idea. Just think of a real click for now.
Okay. In a real click, like if everyone else is colored, I would expect to sample like almost everybody, right?
Yeah, very good point. Yeah, so this algorithm is not efficient at all.
Okay.
Yeah, it's just like that's the problem. So like you're finding a recoloring, but you need to go for delta steps to find it.
Right.
And like yeah, so just one thing I wanted to mention is that like if you think about like this bipartite graph perspective, well, you're really finding an augmenting path. Right? At the beginning, the coloring is like that, and then you've gone like through this chain. And at the end, what you've done is that you match you change it, right? So you found the augmenting path. The only problem is, as you said, we found a very long augmenting path, and we need something more efficient. So how do we do this? Yeah. So let's again one uncolored vertex, and instead of sampling one color, well, you can sample two colors, right? Again, the colors are going to be used. And those guys now sample two colors. And so you can see like that we grow like, go for log delta rounds. And we're going to grow a tree that has like roughly delta leaves, right? Because it's a binary tree. So it's expanding very fast. And once I'm there, well, again, if I find a color for a leaf, I can just recolor the leaf and then recolor the vertex before the leaf and recolor the entire path, including the root. So I just have to show that like it's likely that a leaf finds a color. And well, why is it likely? I have a probability 1 over delta to find the one good color, and I have a delta over 100 leaves. So with constant probability, you're going to find the one missing. Like one leaf is going to find the one missing color, and you just need one leaf, really. Right? And so if you think about what's happening here, is that so we had like a click or this bipartite random graph. And so what it means is that it has like it takes very fast. It's like it has like very low diameter. So it'd be like yeah. So it has to have some like short augmented path. You really don't have to go for this long before you find an augmentation, right? This is kind of like the underlying intuition when you look at the bipartite graph. But I think it's also nice to think of it as simply the colors will be true. Right, and so you can do this when there is also like color in the graph. You don't need like if there is like more than one colored vertex, what happens is that you grow like a bunch of trees in parallel instead of just one, and you need to make sure that the trees are not colliding to each other with each other. And like you don't try to recolor leaves from different trees using the same color, this type of things. you need to be careful. But what happens is that okay, each tree should have like delta over k many leaves, and you have quality k over delta to find the one missing color. So the probability of coloring like this guy is constant. It's the same for every leaf. So you color a constant fraction of the vertices, right? Yeah. Right, and so you just need to repeat this log n times until you get no vertices colored with high probability. That's like the rough scheme of the algorithm. And you can see why we get like a log square, because drawing the tree is going to require log n, if it's like n click. And I need to repeat this log n times to get everybody colored. So it's a log square and random. And just like some notes on this. This is too many words, but so you need to deal with the conflict between the trees. Like this can be done with kind of standard techniques from distributed algorithms. It's not too difficult. It's more like annoying is that you need to make sure the trees are balanced, because like the number of leaves you have in a tree corresponds to your likeliness of being colored. So if you have like one tree that has a lot of leaves, and the other trees have much less. Actually, you just have this one vertex that's very likely to get colored, but not everybody is likely to get colored. You need all the trees to have roughly delta over k leaves. It needs to be balanced. And so this means that like when we grow the trees, we need to grow the trees all at the same time, or at least that's how we do it. And because like if you're not too careful, it could be that like one tree grows much faster than the other one. And the next step is going to again like step on the other trees. And you end up with just one big tree and a bunch of small ones. You need to be careful about this. And we do it kind of brutally by sampling log n many colors. Like instead of, like on the picture here, I have like two edges. And so what we actually do is we sample log n colors here to make sure that with high probability, we're going to find like the same number of edges everywhere. And so all the trees are going to grow at the same speed, right? So like it looks like a technical detail, but it's like part of why we need log square and list size, colors in the list. Because like you grow the tree log n times, and each time you need to sample log n colors. So you get the log square here. I'm not convinced like this is the like absolute right solution, but at least that's how we do it. And yeah, so you have some also like when I stated the theorem at the beginning, I claimed the log square delta rounds, which is slightly better than log square n. It requires some work. I don't really want to talk much about that, but yeah, so like with some extra work, you can show that not only in expectation, but with high probability, a constant function of the vertices get colored each time. So that's at least the algorithm for a clique, right? So how do we make this work in almost clique? Well, the first issue is that maybe the cluster is going to be slightly larger than delta plus one, which means you don't have as many colors as vertices. And so there's a problem if you use colors too quickly, and at the end you don't have enough color left. What you do there, and I mean this was already existent in the panel specification theorem, you color a bunch of vertices using the same color in every clique. And like one intuitive way to think about that is that like, if you confront this vertex, right, you remove one vertex from the clique, and you only use one color. So if you do this enough time, then you pretty much end up in the situation where you have a clique, a real clique, or a clique that has no missing edges on the inside, and with as many free colors as you have in those. Okay, so we had to make this distributed, and this wasn't like the most complicated part, let's say.
Maxime, I think this is the step, right? That is just Maxime management. So the time plus one Maxime management.
Yes. Yes, so
I guess maybe I didn't fully understand. So you're saying if in the total group, we like definitely I see, okay, you can contract those to like green versus there.
mhm,
And coloring for the contracted graph will also be coloring for the almost complete, but
yeah.
how do we know that this will really be keeping as a contraction process and then getting to
You don't get them to complete in SCK actually, as long as you have almost complete that have epsilon delta non-edges inside it. You need at least epsilon delta non-edges inside it, you can find some of that.
yes.
Yeah, because your sampling is enough to each point and point of one of those things. So then when you stop, you have a structure that the number of non-edges inside it is less than epsilon delta. So it's not a clique really, but it will do a bunch of things. For instance, it cannot have size more than delta plus one. Because if it's delta plus two, you mean that it's delta non-edges.
Right.
It fixes it creates a good size on these structures, and then there are very tiny number of non-edges.
Like what's happening really is that you're not really killing all the anti-edges on the inside, like these red things, but you can show that like for pretty much all of the vertices, not all of them, like almost all of them, you know, you're gonna have what you would have in a clip. Like if there's k colored vertices, you have k colors in the palette.
Right.
And that's
you're trying to get.
Yeah, that's like the only thing we want to get. And we don't get it for all the vertices necessarily. We get it for most of the vertices, and this is enough for us. Like, yeah, it's a bit simplistic to think of like this getting to click, but it's pretty much close. It's close to that. Okay. So this was one of them. And okay, so the other one that's a bit more challenging is that also like between all the splits, you might have edges. And so if you do some recoloring here and you do some other recoloring there, and you're not careful, maybe you're trying to conflict. And you really want to avoid that. So how do we do it? And this is like I'd say like the next big part of the algorithm, because when like in the ACK proof, you know, they take one almost click and they color it, and then they take the other one and they color it. And so this really was absent of the previous theorem. So we have to like solve this issue to make it work in context. And we really want something simple. You know, if you try to do something smart for solving the conflicts, you end up trying to solve something more difficult than coloring itself. So you want simple things. And just to emphasize like how bad this is, well, so the nodes are like if you just think of one time border tree, right? The nodes are sampling log n colors just in this one iteration of going the tree. And if you have like so delta epsilon external neighbors, with high probability someone is gonna, you know, pick the color you want to use, right? So it's almost certain you're gonna have conflict. And this is really bad. But what you could do is just like decrease the value of epsilon, because like yeah, if you put epsilon to be 1 over log n, what happens then is that you know that the probability that some neighbors pick the color you're interested in decreases as well, because they just have less sample to try to hit your color, right? So like if you look at this, for instance, like so this is the probability that they sample my color. Like none of them sample my color. I get like the epsilon that's going to cancel the negativity. And so I lose the color with probability of the response. Okay? It should be wasted.
Wait, okay, so they had this problem on something, but if you maybe that's longer a sports vertices, they need to sample the more.
Yeah.
Now they will start creating complete more for this, right? So you first handle the weeks and then go back to sports vertices.
No. So we actually, we can't do that. Like we don't put epsilon investment. We have a trick, but it's essentially getting us back to the situation where we have like the small epsilon. I'm gonna try to explain that just in a moment. Okay, and so then you have to show that like this is like probably the most technical part where you're going to show that like you analyze one iteration of growing the tree in the MSP, right? And you first reveal the color sampled by the neighbors, and you drop any color that was sampled by an external neighbor of yours. Okay. If any external neighbor might use the color to recolor itself, you just forget about it, right? And then you have like two things happening. First, you have the growing phase where you really like any color is good kind of in the growing phase because you just want to expand the tree. So then what happens is that like the external neighbors are only blocking the constant fraction of the color space, so you're fine. You can grow the trees. What's a bit more annoying is that when you look at the leaves, that's what I've called harvesting, like you try to get the fruits of the trees and recolor them. Then you really look for like specific colors. It's just not any colors in the leaf. And so then what we show is that a very small set of nodes are going to be bothered by the external neighbors at this point of the algorithm. Right? So it's kind of like a virgin algorithm. Like intuitively, it's not the complete truth, but like just before I said you lose color with every constant probability, right? So if you do this for all the nodes in parallel, the probability that you're going to lose too many colors from like this specific set of colors you care about should only represent a constant fraction of the field. Maybe this is a bit quick, but like it's kind of that's so you only have like 1% of the clique that's really bad, and because the trees are like, covering a lot of have a lot of the leaves, you're not going to be able to kill many trees. But, on average, like with some averaging argument, most of the trees should have most of the leaves fine. And if your leaves are not spoiled, well, the augmenting path algorithm, augmenting tree algorithm works fine. But like this is kind of the algorithm, you need to be careful about how you condition, what you condition, and things like that. But this is the rough idea. Okay. Yes. So as I said, you can't really do pick epsilon this small. The reason I said you get a algorithm time, because it also puts more problems everywhere in the algorithm. So what we do instead is that we kind of have like a preconditioning of the bits, of pre-processing. And the general idea is that if you have a high external degree, you also sparse. And it's very easy to see like why this is true. If you care about edges to other cliques, right? If you have an external neighbor to another clique, it cannot be connected to a lot of your neighbors of you, right? Because like it's like two different cliques. So there can't be dense connection between the cliques. Maybe I should do a picture. Right? You have some clique, and I have a neighbor to another clique. You cannot have like a lot of connections there, because you must have most of the edges in the piece first, right? So you must have like only few connections there, and so this gives you like what we call sparsity. And sparse nodes are easy to color, kind of. So what you can do now is that like if you're a bit careful, like I don't know how much time I have. I don't really want to get more into the details of it. I can explain it more later. But if you're careful about like the order in which you color the case and like how many nodes with high external degree you have and stuff like that, you can manage to get rid of all the cliques that would have been a problem when you run the augmented tree algorithm. So you're going to end up with a coloring where we know that the uncolored vertices have only delta log external connections to uncolored Everything else is correct. Right, and we only need to run the algorithm, the advantage algorithm in the uncorrected. Right? Well, ask questions if you have questions. But, I don't know if I should spend 10 minutes trying to explain this.
On this also, you do one round of one-shot coloring that makes a sparse vertices low degree. And then so you ignore your low degree vertices now, because they're low degree, you can always combine and color.
Yes.
And then you run the honest split bar and handle them. Because you did just one round of one-shot coloring, you don't lose that on the honest. It's like really long coloring.
Yeah. Well, I guess the issue is that you still have, you still have most of the incorrect fits that are going to run the algorithm. You could still have all of your neighbors, external neighbors, could be two incorrect fits, and this is really like the kind of connection you care about. I don't see how just one.
I see. So if you don't want your neighbors not on the epsilon delta, but you don't want them to be inside the center with also. Like what are backclicks here?
Yeah, so backclicks is like a click where you have just one node that has a high external degree tolerance. Like this would be bad for us. And we only care about these nodes because nodes that are not in our splits are not going to run the algorithm anyway, so it's easier to get it. And so what you can do is that if you have, for instance, a very small number of very small number of those nodes that have high external degree, then you can just color them at the very beginning. If you get rid of them at the beginning, then will be a problem. If you have a bunch of, if you have a large number of nodes like that are very sparse, well, what you can do is you color those first, and then you use the fact that they are sparse to color them just like that. That's what's happening. Those nodes could be difficult to color, but because they have a lot of neighbors that are doing nothing at the beginning, you can color them. And then those are sparse.
So what I was saying, I mean, sparse vertices are not low degree, so you cannot actually color them after you color the rest. You have to first make them low degree and then do color.
Yes, I mean, like the point is that the point is more of those vertices.
No, but ignore that. Like these are sparse vertices if you want to color them at the end. Maybe you start like the reason you put out coloring was that they have two neighbors that didn't have an edge. But maybe you start coloring those things with the different colors. So you no longer the fact that these vertices are sparse is no longer important.
Yeah, because you need to color them at the beginning because otherwise you might need to try to parts slightly. Yeah, it has to be like a really careful on the actually do this. Any more questions on this? Okay, and so this pretty much concludes at least the upper bound part. So we hopefully you have a rough idea of what your game was. And I just want to finish on we really wanted this polylog delta momentum, not polylog. And the reason for it is because we can show a lower bound. So it's not like a super strong lower bound, but it's interesting anyway. Like say you sample a list, and it could be any polylog n size. You log to the 20, log to the 100, doesn't matter. And then you just run a local algorithm, but only on the Sparsified way, only using those edge list data sets. Right? And this is why the lower bound is kind of weak, because you could design an algorithm that's not doing this. But if you just use an algorithm that does that, then you have like a lot of delta level, roughly. And the reason is not so complicated, a high level at least, because so as we said earlier, you're trying to compute a perfect matching in this one. And perfect matchings are really not local problems. If you think about like a long cycle, right, and you're trying to compute a perfect matching, well, you have two perfect matchings, and nodes that are far apart in the cycle need to agree on which ones are going to choose. So for like a cycle, it's easy to see that for arbitrary graphs, it's easy to see that we need to spend diameter time to solve the problem. But the one issue here is that it's a random graph. So it's not really like an arbitrary graph. But you can show that even for those random graphs, it's not a local problem. But you need to synchronize far away from each other. And so, which means that intuitively, it's not really the full argument. But intuitively, you need diameter time. And in this random graph, the diameter just happens to be like delta W. The log delta just comes from the size of the clip, and the log log from the polynomial sample. And so we have like that, like a kind of a nearly optimal algorithm for at least what we try to do. So this
load bound if even if I allow every order log and additional entries or twice we communicate on
I don't think so. But if no,
because you said it's just based on the diameter.
no.
I see.
Yeah.
You can reduce terms that are not like this. And we can figure out it's an anonymous split and ask everyone else to connect with it.
No order log and
So everyone is on your
I don't think the lower bound works. It's really like based on the fact that the graph is use the random, like the sample values. So like if you allow any kind of like more relaxed assumptions on how the graph looks, it works automatically. It's kind of unsatisfying. Like it's nice in the sense that it shows that at least what we try to do is like almost as good as it can get, but it's not a strong lower bound for the question I had at the beginning. Like coloring without talking with many numbers.
I think it didn't handle this. Is that everyone is connects to log and all the family member? You just increase the size of the amount of logs.
not log and neighbor
Inside, yeah.
process. But it's a way to it's a otherwise captured in the
There might be a way, like if you have to choose, the edges deterministically before really looking at the graph or something like that. Maybe you can somehow extend, but because this is giving very little power to the nodes, maybe somehow you can extend that. But if they can choose the edges somewhat adaptively or be a bit smart about this, I'm not sure this the lower bound is going to extend.
Yeah, I would be surprised if it's due to them independently of the sampling. Somehow there should be a way to perhaps make the load down. But if it is done after sampling to compensate for the events that arise due to sampling, then I suspect your load bound may not hold. But otherwise, I don't know.
Yeah.
Anyway, it's speculation.
Right. So let's just recap quickly. We have a distributed version of the Sparsification theorem, which uses slightly more colors. It's not really a big deal for the algorithms, for the applications. And it tries in polynomial delta 1, which is nearly optimal for what we're trying to do. And yeah, so it has some applications, and I think we had to came up with a bunch of techniques that could be interesting for distributed algorithms in general, especially for like how the color is decided by looking at the randomness inside, trying to show like how to the kind of conditioning we can make and these types of arguments. I've not seen that like in a lot of places for distributed algorithms. So maybe these ideas can be pushed further for other problems. Okay, and so I'm just going to finish with a bunch of open problems. So you could look about like harder types of coloring. So if you, for instance, if you have like, okay, degree plus one is coloring, is just the number of colors you have depends on your degree. If I have degree 10, I have just 11 colors in the list. If I have degree 100, I have 101 colors. And when I put list, I just say, it doesn't have to be numbers from 1 to 10. It can be any number from like 1 to n to the 100, for instance. Right, so like even describing your list to your neighbors, it's not clear how you do this. It's not even clear like how this question actually totally makes sense, because you need like, to know the list of your neighbors. So like that issue with this. And yeah, so you also could ask for delta color. I think Sparsification is not enough for delta color anymore.
Yes, I know. I mean, it handles all interesting cases, and then there was some that it characterizes. In this paper, it was like it characterizes the cases it does on the board.
Yeah.
And there are like 6, 7 various which are correctly. But then you have to handle it yourself.
Yeah. Yeah. So yeah, you have to do something similar, I guess, if you try to do delta coloring with these types of algorithms. Yeah. And anyway, you could also like try, so for our applications, we could ask, okay, can we somehow prove that the lower bound holds, or can we beat the lower bound? Can we do something smarter in Sparsification? You could ask about trade-offs between like the number of rounds you use and the size of the number of messages and the size of the list of events. So there's a bunch of questions that are left open and could be interesting to look at. And that would be it. Yeah. Thank you.
Ask one other thing. Do you get anything around the number of random bits or using? Is there a bound that are
Bound better than per node, you mean?
yeah, like so no, I mean you're using n polylog or like our SK paper needed n polylog, and I don't think our argument would go through better than the binding times because of this random ground order we are doing on our own because I don't know if yours can give you polylog del binding times.
So yeah, it's a good question. I've thought about it a bit. I think the augmenting tree algorithm should work with just log n wise independence. And so like because you can make if you really don't try to delta every time, then you can just look at the expectations, show that it like it works fine on expectation, and get this to work. And so like something like log n wise independence should be enough there. You still have problems with the sparse vertices. I don't know how to deal with sparse vertices without like a lot of randomness, a lot of independence. Because like this one-shot coloring where you say that sparse vertices get slack. I have no idea how to use mass randomness for this.
Right. Also, I don't know in derivatives the thing, but in classical STP you can do that with pair d log and words, so maybe then pair was. We don't want to solve it. Then maybe to combine this thing and like without this derivative aspect, you can get a small number of times.
Really? Okay. Yeah, so we have to talk about this. I'm interested. Because the probabilistic argument is like at least distributively when it's complicated uses like complicated concentration bounds. So yeah, we talked about this a little and we couldn't find ways to get rid of it. Maybe it's because we tried to do it distributively.